what they are. Let me just I need to share my iPad soon. Okay. Okay. So one of those files is a here. Okay, I have it here. It's like a summary of the distributions. The formulas, different cases. I'll tell you what this is, how to read it. I'm hoping that this will be helpful when you're going through the problems in section C and B. This is called, I think, table of distributions or distributions table file in Canvas. And then I also added something I'm going to use today that's called Pascal-like triangles. I'll tell you what those are. So going back to this distributions table, let me see. We did a little bit of it before. So this table that I was trying to complete last time is part of it. So you will recognize that I have the n to the m, these combinations with repetitions that we have here, the t numbers, the partition numbers, and the Stirling numbers. So in this new table, here you go. So here you have the n to the m. So same idea as before. I have either I have a certain number of balls, a certain number of boxes, and if you want, it says so here, it's n balls and n boxes. So maybe you want to include it here, n box and n boxes. I have all the different options, same as before, different, identical, different, identical. Okay, so it's the same as we had earlier. But now I have some other examples of problems that you can identify with these standard ones. So for different balls into different boxes, we decided we could do this n to the m, and then I had the theorem from last time that is this identity. So here I have 3 examples where you can use this same idea. You could be counting strings of length m using elements from an n set, meaning you have n different letters available, and you are counting strings of length m, repetitions allowed. So that's the same as thinking about the boxes as the letters. Think about it as having n equals 26, for example, all the letters of the alphabet, and you're looking for words of length 10, let's say. So because you allow repetitions, you essentially can think of having boxes with A's, a box with B's, a box with C's, and so on. So your boxes are the letters. And now you want to use exactly 10 letters. Some boxes can be empty. And the total number of letters that you use is 10. So that goes with this application of this number. The n to the m comes from the first letter in your word can be any of 26. Your second letter in your word can be any of 26. So this really is like just the very first application we saw of the fundamental theorem. But here's another application. Let's look at this one, for example. The number of functions from this m means the set of integers, positive integers from 1 through m. So this is the functions from the set 1, 2, 3, 4, 5 all the way to m to the set 1, 2, 3, 4, 5 all the way to n. So how do you count those functions? You can think of the images as the boxes and the the domain as the balls. You have m different balls going into n different possible different locations, the codomain. And so the number of such functions is just going to be n to the m. So this is what we had earlier. This would be, if you want to relate to our previous table, is empty boxes allowed. So we had this one, and we had this one, and then I added other columns. So we have that. These are just examples. These are just examples as well. And these are kind of the explanations in terms of numerical partitions. So we kind of had that. So here you have the T numbers, here you have the Stirling numbers. I think that I reversed these two. So here I have the numerical partitions, and I think in my previous table I had numerical partitions first and then Stirling numbers. So these two are reversed in the previous table. But what I wanted to show you is this one, because I told you that I wanted to have a few more examples of like the first problem in the class activity. Those go with this. So this is, look, a specified number of balls per box, and my balls into the ith box. In all of the others, we didn't specify how many balls per box. We just said we have a total of a total of n balls into a total of n boxes, but we didn't say exactly how many balls will need to go into each box. But these parts, these multinomials, were kind of all the possibilities, all the, going m1 balls going into the first box, m2 balls going into the second box, and so on. So these multinomials were like all the pieces that will give you the t number together, right? And so that's what this is. These are the pieces of the t numbers. So if you tell me that you need to have exactly 2 balls in the first box, exactly 3 balls in the next ball, in the next box, and so on, then you're going to use these numbers here, and it's just going to be a multinomial. And if the boxes are available, then you're supposed to use this one right here, where the factorials you're dividing by are the multiplicities of the numbers that, the sizes, the number of elements in each box. So just to fix ideas, let me show you how we use these in the class activity, in the first entry, in the first problem of the class activity. Let me see, I think it's in the previous page. Yeah, here. So this was the class activity. These are what I called at that time, partitions of type 1133. You see, here we had identical boxes, 8 different balls. And so I told you, you need to choose. Imagine for a second that the boxes are different. So you need to choose, because we wanted to have, this type of partition: 1 ball in the first ball in one box, another one in another box, 3 in another box, and 3 in another box. Then what we do is we choose, this 8 choose 1, 1, 3, 3 just means we're choosing, if this is the same as 8 choose 1, and then what remains you choose another one, and then from what remains you choose 3, and from what remains you choose 3. So that will be the answer. The 8 choose 1, 1, 3, 3 will be the answer if the boxes were different. But because the boxes are identical, when the boxes are different, then you know exactly you want this exact distribution. Okay, but since the boxes are identical, we need to divide by these two boxes are kind of counted the same, so we divide by that 2 factorial, and then we divide by this other 2 factorial, because there are 2 boxes that behave the same way. So these factorials go we divide by these factorials. These are the multiplicities, right? 2 1s, 2 3s. So we divide by 2 factorial, 2 factorial. Identical boxes, different balls. So let me go back to that table here. So that's what this is saying. I'm specifying exactly how many balls per box. So that would be the 1133 here. And then, because my boxes are identical, I need to divide by the multiplicity. So that's what the R's are here. I'll show you some examples, but that's what this column is. It's like the pieces that make up the full Stirling number or the full T number. And those can be used when you are given the exact number of balls per box that you need. So let me give you some examples. Remember, is this multinomial or the multinomial divided by the multiplicities? Okay, so I'll give you some specific examples. So which one was small section? Okay, so for example, oops, what did I do? I think my cable is loose. Okay, so I'm not going to tell you which problem number it is. That gives away whether we're doing partitions or distributions. So let me say number of partitions. Number of partitions of a 10 element set of type 1 1 1 2 2 3. Okay, so when they say partitions, you should think of identical boxes. So you just need to group your objects, but they don't go into a label box. You just make groups, which is the same as having identical boxes just to separate the objects. So you have a 10 element set. That's going to be your M. So the number of balls. And you're given a specified number of balls per box. So that's that column I was talking about in the table, right? So let me just go back very quickly to the table. That's what I'm talking about here. Specify number of balls per box. That's what this means. You have 1, 2, 3, 4, 5, 6 identical boxes. 6 identical boxes. And you need to have exactly one here, exactly one here, exactly one there, exactly one there, exactly two here, exactly two here, and exactly 3 there. But the boxes are identical. So you should think of this as a partition of a set. So, you have a set of 10 elements. And so, you just want, the elements are different, but you just want to divide so that there is one here, one there, 3 in some other one, another one, 2 twos, and that's it. That's how you want to divide it. But your objects are actually different. So maybe instead of dots, I should be using, then I have different partitions, right? So this one could be a 5, this one could be a 7, an 8, if I actually had like the digits, right? Which there's 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's one partition. So even though I'm thinking of 6 boxes here, they're not really boxes. They're just kind of grouping the stuff to take it someplace else, but they're not labeled or anything. Uh-huh. So this goes with the Stirling numbers, or these are like this is one of the pieces that makes up the Stirling number 106, and it's just going to be the multinomial 10, because we have 10 objects, and we're supposed to choose 1, 1, 1, 2, 2, 3. And it actually doesn't matter in which order you list those numbers. Uh-huh. The multinomial is the same. And then, because the boxes are identical, I'm going to divide by the multiplicities. So I have 3 ones, so I divide by 3 factorial. I have 2 twos, so I divide by 2 factorial. And I have 1 3, so I divide by 1 factorial. Not that that makes any difference. But just to be consistent, why not? I'm just going to write the 1 factorial there. Make sense?
Professor, is it 1 factorial 3 times? If it was a different case, is it going to be 3 times something?
Now, this is the 3 here is because there are 3 ones. So there are 3 groups that have the same property, the same number of elements. So the 3 is because there are 3 ones. So you're dividing by the factorials of the multiplicities. How many of each kind there is. In other words, the reason why I'm dividing by 3 factorial is because this partition that I have here, this example that I gave you here, So this one, this partition, and I know that the numbers are tiny, so let me duplicate it. Yeah. As partitions, right now, of course, they're the same. But if I switch these, I think this top one was a 5. So if I switch the 5 and the 9 here, they're the same. They're the same partition. And this is also the same as if I switch, for example, here the 9 and the 0. No? So instead of having here the 9 and here the 0, I could switch the 9 and the 0. And I can also switch I don't know, I could also have, maybe I should have been more consistent. So 5 and I could also switch 5 and 0. So I can have 5 here and 0 there. And I can also switch, I could have the 9 here, the 5 here, the 0 here, and the 9 there. 5, 0, 9. So all of these are equal. And I could also have, let's see, I have one more. The 0 here, the 9 here, and the 5 there. So 0, 9, 5. See, I'm kind of focusing on the 3 boxes, which are really not boxes, they're groups, right? So I'm focusing on those that have exactly one element. And the order is irrelevant. The boxes are identical. I'm just making groups, right? So saying 9, you're going to be by yourself. 5, you're going to be by yourself. And 0, you're going to be by yourself. It doesn't matter in which position you place them. This is 3 factorial. But the thing is that the multinomial is actually kind of counting in how many ways can I fill in this spot. In how many ways can I fill in this spot? In how many ways can I fill this spot? And so on. So it's counting as if we had different boxes. But in reality, all of these things are the same, and there are 3 factorial of them. So that's why we divide by 3 factorial. Mm-hmm. And then I could do the same if I look at the ones with 2 elements each. These ones are kind of playing the same role. And I could also just, for each of these, I could just switch the 4, 6, and the 7, 8. And so, I'm repeating. That's why I'm dividing by 2 factorial. And, the 1 factorial is for this one, but since I only have one, it's like I don't even need to divide by 1 because it doesn't do anything, but I write it so that I'm consistent with the multiplicities. Make sense? Mm-hmm. When you have different boxes, let me make the equivalent problem to this one. Let's say that now you want the number of ways to distribute 10 people into classrooms, A, B, C, D, E. So 1, 2, 3, 4, 5, 6, so that it's more or less the same problem. So into 6 classrooms, so that there are one person in room A, one person in room B, one person in room C, 3 people in room. Actually, I should do 2. I'm just gonna go with 2. 2 people in room D, 2 people in room E, and 3 people in room F. Okay? So now my classrooms these are actual classrooms, and they're labeled A, B, C, D, E, F. They're different. And I still want to have one person here, one person here, one there, 2 here, 2 here, and 3 here. The people are different. This is my M. That's the equivalent to M different balls. And this is my N different boxes. And we have this is a specified number of balls per box. So that's again that column of my table. But this is a part of the T numbers because this time around I have different boxes. And the answer for this one is just going to be 10 that I have to distribute exactly into these sizes. But this time around, I don't have to divide by anything because it is not the same to have, I have my boxes. And let's say that I had person, I'm going to label them as person 9 here, person 3 here, person 0 here. Person 9, the 9th person goes to room A, the 3rd person goes to room B, the 0 person goes to room C. You see, 4 and 6 go here, and 7 and 8 go here, and 1. Oh, this was supposed to be 5. Sorry, I'm trying to go with the equivalent to this distribution, this partition. Okay, and so here I have P1, P2, P3. Yeah. So you see, that's the equivalent to my first partition with my first That's equivalent to this one right here. And this time around, this is different from having, let me go with the second, with the second one right here. This time, this is different from having P5, P9, P0, P4 and person 4 and 6, person 7 and 8, and people 1, 2, and 3. See, this time they're different. That's why this time I don't divide by anything. So this is my answer here. This is my answer there. That's what going from identical boxes to different boxes, but in both of them you have a specified partition. And let me give you one more example. So this is 1, this is 2. And so let me give you one more example, which is when I specify the numbers, the rooms are still different. I specify the numbers 1, 1, 1, 2, 2, 3, 3, but I can have 3 people in the same in room A, let's say, instead of room F. So number of ways to distribute 10 people into the classrooms. So same as before, A, B, C, D, E, F, 6 of them. So that there are 3 people in one room, um, 2 people in each of 2 rooms, and 1 person in the remaining 3 rooms. So the difference between problem 2 and problem 3 is that in problem 2, I told you exactly 1 person in room A. Here, I could have other, I could have, this is still okay. This is still one possibility. But I could also have 3 people in any room. I could have 3 people in room C, I have 2 people in room A, and 2 people in room E, and then 1 in the others. That's another possibility. Make sense? And I have plenty of other possibilities.
There's a question. Empty boxes are allowed or not? The entire thing we are doing. From example 1 to 3.
Oh, thank you. Yeah, that's a very good question. Let me just say no empty boxes allowed, because that's well, actually, you know what? Yes, there are no empty boxes allowed because I specify how many in each box, right?
Oh, I see. Okay.
Yeah. So I don't really have to say it, but that's a good question. That's a good comment. So yes, in this case that I'm specifying exactly how many in each, I could specify that there is an empty room, for example. So I'm actually allowing empty boxes, but I will say that, I'm saying exactly how many in each. So yeah. So here I have many possibilities. You see all the different permutations of the ones that 3 1s, 2 2s, and 1 3 are now fair game. So the answer to this is going to be related to that column, but so I'm gonna do this, but this time around I'm going to multiply times the number of permutations. You see, the thing is that this one will give me the answer 10, 1, 1, 1, 2, 2, 3. And this one will give me the answer 10, 2, 1, 3, 1, 2, 1. But these two numbers are equal. These two numbers are equal to 10 factorial over 1 factorial 1 factorial, 2 factorial, 2 factorial, 3 factorial. And that's obviously equal to whatever order I place my factors in the denominator, right? So any of these choices that we make here, I can write another one. Any of the choices that we have here is going to have the same answer. A, B, C, D, E, F. I could have the 3 people in A, 2 people in B, 2 people in F, and 1 in the other rooms. I could have something like that, and that will give me this multinomial 10, 3, 2, 1, 1, 1, 2. But that's also, the same as the others, is equal to those. Mm-hmm. Because it's just a rearrangement of the factors on the bottom, but we know that gives exactly the same result, right? So the only thing I need to do is how many of these I have here, and I'm going to multiply times that here. So the number of permutations of 3 1s, 2 2s, and 1 3. Here I'm actually going to multiply times I'm going to multiply times 10 factorial. 6 factorial. 3 factorial, 2 factorial, 1 factorial. This is the number of rearrangements of 3 1s, 2 2s, and 1 3. Yeah, so, rearrangements of 1 1 1 2 2 3, which is this over here. So we're still using that column, but we're using it many times. That's what we get. So those are kind of the 3 problems that are kind of related to each other, but depend, on what we're giving. The difference between these 2, problems 1 and 2, and the third one is that in the first 2, I'm actually saying how many in each specific box. In this one, I have actually many possibilities. The numbers are fixed, but those numbers can go for the different boxes. Okay, any questions? I'll upload this to Canvas in case, you didn't get to copy everything or you're missing something in your notes. All right? Okay. So, take a look at the table, see if you have any questions. We'll talk more about it for the specific parts on Tuesday if you want. There are, in the book, you have these other 2 functions. You have these other 2 functions. These are these are also numerical partitions. These are numerical partitions, but these are numerical partitions where all the parts are different. And again, we don't have formulas for that. These are numerical partitions where all the parts are different. That's what the star means. And these are numerical partitions where all the parts are at least k. So I'll talk more about these 2. I don't think there are any problems, or if you've seen your problem, I don't think I selected any problems that use the p star or the piece of k. Not that they're not interesting or important, but I just didn't assign them. But if you did get it, let me know, and I can make sure to, help or move the due date for a different date. Okay. So, questions. All these other columns are, variations of the problems. For example, here it was a specified number of balls per box, and this is at least k balls per box. So now you need to, that's a variation of the problem. And as you can see, the only thing that changes is that we won't be able to use that formula because the solution to this is part of the t number, but not the full t number. But if you look at the definition of the t number in terms of multinomials, you can see that, this is just part of that definition. Here we're saying that all the parts are at least one, each of the boxes gets at least one ball. And here we're saying that each of the boxes gets at least k balls. You see? So these are just variations. This is different number of balls in each box. Then you actually need to go with this formula for the t number, but you don't include all of the multinomials. You only include the ones where all your selections here on the bottom, the numbers on the bottom are all different because you are asked to have different number of balls in each box. So these are just variations that can be obtained from the definition of that number. Same thing for the Stirling numbers. This is the full Stirling number. And, in the full Stirling number, you are using, you can, if you need the full Stirling number, then you can use the formula for the t number divided by n factorial, right? So you could use that formula, which is that dot product that I talked about last time, and then divide by n factorial. An alternative definition is using what I just showed you, these multinomials divided by the multiplicities. Mm-hmm.
Question?
Whoever,
I just want to make sure when it says like this certain keyword about different number of balls in each box, is that implying different boxes, or it can also be identical boxes?
It could be either problem. So it could be either situation. So for example, let me add another example here. So I could ask you to find, the equivalent to problem 1, right? So I can say problem 4. I can say number of partitions. Number of partitions. I'm just going to make it smaller so that of a 6-element set where all into exactly 3 parts, all with different numbers of elements. Mm-hmm. So, so here your M is 6, and you need to have exactly 3 parts, so 3 non-empty parts. So this is your N equals 3. This exactly meaning that you have 3 boxes, no empty boxes. Okay? And this is the key word that you were asking about, Sean. So different numbers of elements in each box. So this time I'm not actually specifying exactly like in the previous one that it has to be 1, 1, 2, 2, 3. But in a way I am, because I need to have, I have 3 groups I have a partition of 6 elements, and I need to have different number of elements per box, right, per group. And if I need different elements, the only way that I can do it is like this: 1, 2, 3.
Morning.
Mm-hmm.
Sorry, it was just my dad saying morning.
Yeah, so that's the only partition. So because it is the only partition, then I will have this same answer here, like a similar answer to what I had before. So that would be 6, 1, 2, 3 divided by 1 factorial, 1 factorial, 1 factorial. Mm-hmm. But if I change, if I change so the same problem, but with so let me change the 6 to a 7. Okay, so number of partitions of a 7 element set into exactly 3 parts, all with different number of elements. So the same problem, but I just changed my M to 7, right? That's the only thing. So now I can have different partitions. So the total is 7. I'm supposed to have 3 parts. So I can have one part that's 1. The others need to add up to 6. So I can have 2 and 4. Why is it not working? I can have 2 and 4. Or, can I have more? Maybe, sorry guys, let me change it to 8 because I don't think I'm going to have another. It's not a good example because I'm not going to have, I was thinking 1 and 5, but then I will have repetitions. So I'm just going to change that to 8 because this one for sure, I think, will work. So 8. So I can have one box with 1, and then I have 7 left. So I can have 2 and 5, or I can have 3 and 4. So 8 total. And I don't think I can have anything else because if, those are my only ways of making 7, not using 1, right? So 1, 2, 5, 1, 3, 4. And if I don't use the 1, I will need to have 2 here and then a sum of 6. But to have a sum of 6, I can have that, right? That's another way to add up to 8 with all different numbers. 2, 2, 4, 3, 3. That's the only one because I could also have 2, 2, 4, but then I have 2 that are equal, or 3, 3, 2, but then there are 2 that are equal, so I don't want to use those. I think that's it. And so that means, these are partitions of numbers, right? Here, I'm first looking at all the different ways that I can write 8 as a sum of 3 different numbers. And by the way, that's the number of partitions where all the parts are different of 8 into 3 parts. So these are numerical partitions. This is 3. So this is just in how many ways can I write 8 as a sum of 3 different numbers. So I can have 1 plus 2 plus 4. I can have 1 plus 3 plus 5. Or I can have 2 plus... Oh, wait a second. This one... These two are the same, right? These two are the same, 1 to 5. So not that one. So this is the same as the previous one. So this is just 2. This star means number of numerical partitions of 8 into 3 positive integers into 3 different. That's what the star means, different positive integers. And those are the only 2 ways, right? 1 to 4 and 1 3 5. The other one that I had was just a different order. 1 2. What am I saying? 1 2. Oops. 1 2 5. Sorry guys. 1 2 5. 1 3 4, and that's it. 2 3. Yeah, that's it. Those are the only 2 ways, right? And so the answer to my question is going to be 2 of these. So it's just going to be 8 1 2 5 plus 8 1 3 4. And because they're all different, I really need to be, the formula that I'm using is supposed to divide by multiplicities. But because all of those are 1 factorials, because all the numbers are different, the numbers on the bottom, I don't really need to have those. And so this sum that I wrote here, the sum of binomials over the multinomials over the multiplicities, is what I mean in my table. Let me go back to the table very quickly. It's what I mean in my table here. It's different balls into identical boxes. So these are the Stirling numbers. The pieces of the Stirling numbers look like that. Those are the multinomials divided by the multiplicity, the factors of the multiplicities. And what I'm saying here is that the summation goes over only the possibilities. Oh, not that one. This one here. Only the possibilities where all the bottom numbers are different. And to make them all different, I have strict inequalities here. So I'm just placing them in increasing order as I did in my problem. So it actually goes with this one. Is different number of balls in each box, no empty boxes, and if you look at on this side, here we have different balls, which you can think for some of the problems as people going into groups. Different people going into groups that don't go in a specific location or anything. It's just a group. So identical boxes. So different balls into identical boxes, and I have different number of balls in each box. So this formula looks very much as the one for the Stirling number, but the summation goes over a restricted set. That restricted set is that all the MIs, all these bottom numbers right here, are different. I'm looking at this one. They're all different. So to make them different, I just place them in increasing order, and it needs to be strictly increasing. They're all different. So these extra columns are just like specific cases of the ones that we did earlier, just like pieces of the T numbers, pieces of the Stirling numbers, and so on. But you need to practice with the table and see if it helps you. All right? Okay. Any questions? Okay, good. Thank you, Noah. Oh, by the way, Noah, I'll do that. Your email. I'll do it for this weekend. Okay. So that you have it. Okay. All right.
Okay,
so
thank you.
no problem. Okay. So let me now show you something else. Some of you have problems. Several of you have problems that are complete the first 4 lines of the T numbers triangle, or your problem refers to completing a triangle, a Pascal-like triangle. So that is related to the fact that all these numbers, the binomials is the first case, the binomials that we use for the combinations, create a Pascal triangle. And the reason why they create a Pascal triangle is because they satisfy a recursive formula. Well, it turns out that the T numbers, the Stirling numbers, the numerical partition numbers, even these ones that are special, where all the numbers in the partition are different, or all the numbers in the partition are greater than or equal to something, all of those satisfy recursive definitions. So recurrence formulas. So I'm gonna, and therefore you can create a Pascal-like triangle. So that's what I have for you, prepared for you. I'll make this fit in the page when I upload it. Okay, so that's what that's why I have these Pascal-like triangles. Okay, so for the binomials, what's what we know? This is the one that we all know. This is the original Pascal triangle. So the definition, what it means, what the symbol means, is the number of ways to choose n objects from m available. We know that choosing 0 objects, there's only one way all the time, or choosing all the objects, that would be m choose m, there is only one way. So it's like the cheese pizza and the all toppings pizza, only one way. So those are the initial conditions of our recurrence relation, our recursive formula. And the recursive formula is this, that if you want to get m choose, the number of ways of choosing n objects out of m is, you reduce your number of objects in 1, that's the n minus 1 choose n minus 1, and then n minus 1 choose n. What this means is this, this is like the rule to create Pascal's triangle. This is saying that if you take 3 choose 1 plus 3 choose 2, it should give you 4 choose 2. If you take 3 choose 2 plus 3 choose 3, it should give you 4 choose 3. And you can check this algebraically, see that it is the same. But there is also a combinatorial explanation that this works. The number of ways to choose n different elements out of m available is the same as, you make one element special. Just to explain this, so to combinatorially explain this formula, let's say that you are selecting objects from the set 1, 2, 3, 4, 5, all the way to m minus 1 n. You're supposed to choose n of them. Your n is less than or equal to m in this case. So how you can do it? You can do it in 2 ways. You have those combinations that contain your last element. So we're going to make our last element special. So you have those combinations that contain m. And you also have the combinations that do not contain m. And so how many of each do you have? Well, if they contain m, you already use one of the, you already have one of the n elements to be chosen. So now you only have to choose m from the n minus 1 remaining elements, you choose n minus 1. So what this means is from this set, choose n minus 1 elements. Together with n, you get your subset, right? With the last element. That's how you get your n elements, right? And the other way, so the other combinations are those that do not contain m. So that means that from the remaining n minus 1, you just choose n minus 1. I mean n, sorry. So your combinations are not using n. So that's one way to explain that, if you have m available and you want to choose n, then you can choose those that contain the last element and those that do not contain the last element. You do that separately, and that gives you an identity. That's a combinatorial proof of your relation, your recurrence relation. Mm-hmm. And so we can do something like this for the T numbers, for the Stirling numbers, for the partition numbers, and then create our triangles. And so each of those recurrence relations will give you a rule. So this is the rule for the binomials, the usual Pascal triangle, right? And so that's how you obtain, because of the initial conditions, you know that all of these are ones. I'm just going to write it below, right? Because of the initial condition, all of these are ones. That's just the initial condition. And because of the recurrence relation, you obtain, so your recurrence relation is this formula, this rule over here. And so that means that here you just add 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 1 is 4, and so on, right? And you can keep going. Okay, so that's kind of looking at the usual Pascal triangle in a different way, or understanding how it is formed so that we can generalize it. Okay, so ready for the next one? Let's do the one for the T numbers. Okay, so here we go. So for the T numbers, the definition is right here. Is the number of ways, remember, different balls into different boxes. So number of ways to distribute m distinct balls into n distinct boxes, no empty boxes allowed. That's the definition, okay? So let's see, these are my initial conditions. Let's see that these are actually okay. This one came up last time, remember? That I wrote it down, that the T number M1 is always 1. Why? Because here you have m different balls into one box. You just put all there's only one way to do that. You just put all the balls into the one box. So one way. Mm-hmm. And so what is TMM? Let's understand it. It's m different balls into m different boxes, no empty boxes. So that means that each box has to contain exactly one ball, right? So each box gets exactly one ball, right? And so how many ways can you distribute the objects then? You can position your M boxes and then just permute your objects. And every permutation gives you one assignment of one box into one ball per box. So that's m factorial. Yeah. So that's how you know that, here I'm just going to say each permutation of the balls gives an assignment. Okay, so those are my initial conditions. Once I have my initial conditions, then I know these numbers. Look, for my Pascal triangle, this is a 1, this is a 1, 1, 1, 1, 1. This time around, these are factorials. So this is 2 factorial, which is 2. This is 3 factorial, that's 6. This is 4 factorial, that's 24. This is 5 factorial, that's 120. And this is 6 factorial, that's 720. Okay, and now how do we get the other entries? The other entries are this recursive formula. These we can explain in a combinatorial way. So this is the formula. What you do, if you want to know what's the T number Mn, you're going to consider like the previous two, almost as in Pascal's triangle, Tm minus 1 n minus 1, Tm minus 1 n. See, the pairs n minus 1 n minus 1, n minus 1 n are the same as these pairs, n minus 1, n minus 1, n minus 1 n. You see? So as pairs, they're the same, but this time around is not just the sum, it's the sum, but then we multiply times n. Okay, I'll try to explain this recurrence relation, but before doing that, let me try to use it. You see, the recurrence relation says if you have A and B, so that would be, this one would be like your A, and this one would be your B. So this is A, and this is B. That would be like the entries in one row. And this is the entry in the next row, right? So the entry in the next row is n times A plus B. Okay? So that's my rule right here. So Tn minus 1 n minus 1, Tn minus 1 n. I adding them up and multiplying times n gives me the entry right below. So what I do here to compute the T32, I need to do the sum as in Pascal, as in the regular Pascal triangle. 1 plus 2. That would be the usual Pascal triangle, right? But then I need to multiply times n. And the n in this case is the second number right here, the 2, the second entry. So I'm just going to do it like this. So that's that 2. Is what's extra to what we usually do for Pascal's triangle, for the original one. Make sense? So, for instance, to obtain this one over here, so this one is 6, right? So to obtain the next one, I do 1 plus 6. That will be the usual Pascal triangle. But then I need to multiply times 2. That's the second entry of the one I'm trying to get. So this one is 14. Let me just, I have my completed T triangle someplace over here. Let me just make sure if I make a mistake, I can see it right away. Yeah, 6 and 14, perfect. And then for the next one, see, the usual 1 plus 14, and then I multiply times 2 because 2 is my second entry right there. So this is 30. All right. What about this one? So this is the usual sum, 6 plus 6. That will be the usual for the regular Pascal triangle. But this time I multiply times 3 because that's n. Not times 2, but times 3. So this is 12 times 3, 36. All right. Any questions? Okay.
So
How'd you get 6?
Okay, so Sean, first the sixes come from the 2 entries above, right? And as in the usual Pascal triangle, you have to go row by row to get to the one that you need, right? So
I mean like the 6th part of let's see here, because I noticed it's also But yeah, actually, it's only
Oh,
like there.
this 6 comes from there, right? So I need to add these two. This is 1, this is 6. So 1 plus 6, as in the regular Pascal triangle, this value plus that value, 1 plus 6. And then the 2 is just the second entry of the number that I'm trying to get.
Oh, if this is like a quicker way to do Pascal's triangle, I think I prefer the other way with using binomial theorem.
Of course.
Coefficient.
Of course, but imagine that you want to solve a problem whose answer is a t number. You need to know how to compute that t number. This is a way of computing t numbers using Pascal's triangles. Pascal-like triangles, yeah. So for example, if you had a problem whose solution is T64, then you could, instead of using the formula that I showed you the other day, or, you could compute all these numbers. What am I missing? I'm gonna need this one and this one, so I'm gonna need that one and that one, and this one and this one. So I'm almost there. I just need to compute, if you wanted 3 more. So if you wanted to know what is T64 for a specific problem, I don't want to continue too much longer because I know that there are some problems that say complete the 6th row of the T numbers triangle or something like that. So, but if you wanted to know what is this one, you could keep going. 36 plus 24 times 4, 14 plus 36 times 3, and then whatever you got here, just add them up and multiply times 4. That will be your answer for the T64. So it's just Pascal-like triangles are just a different way of computing, the T numbers. Now, for the T numbers, we do have a formula, a short form formula that I gave you last time, the one with the dot product. So that's easier. But for the partition numbers, we don't have one. The only way that, the numerical partitions, for the numerical partitions, the only way that we have is to actually find all the partitions. So the Pascal-like triangle is very useful because that way you don't have to find them all. So let me, since we don't have that much time left, let me show you the next ones. And then next time, maybe I'll try to explain the recurrence relations, okay? So the next one looks like this. The initial conditions are ones on both sides. So at the beginning, this Pascal-like triangle just looks like the original. All of these are ones. All of these are ones. Those are my initial conditions right here. And the recurrence relation is this over here, which, if you like a visual on how it works in the triangle, you, instead of just adding the two numbers, you first multiply the second number times n. N is, again, the second entry of the number that you're trying to compute. Okay? So, for example, if you wanted to get this entry, the S32, the usual Pascal triangle will be 1 plus 1. But the number triangle, then you're going to have this times 2 in that second term. So this is 3. Make sense? So if you wanted to compute this one, let's say, S for 3, then what you do is, I have the 3 and the 1, so it will be 3 plus 1. That will be the usual, right? Just 3 plus 1. But this time around, I need to multiply times that. The second term is multiplied times the 3. So this time around, this is 6. If you want this one, that would be, the usual would be 1 plus 3. But because this is a Stirling number triangle, we need to multiply times that second entry, 2. So 7. And you can keep going. Again, I'll explain the recurrence, like how do you get these? I'll explain next time. Yep. So that's the Stirling's numbers triangle. You can keep going, and you should have those triangles by the weekend. And this one is harder. This is for the numerical partitions. For the numerical partitions, it's kind of crazy, but there is still a way of doing it. You see, the thing is that the initial conditions are the same as in the usual Pascal triangles, so all of these are ones. And you can think about them, the number of ways to partition the number, for example, here, the number of ways of partition the number 6 into one part. So in how many ways can you write 6 as a sum of one integer, one positive integer? Just one. In how many ways can you write 6 as the sum of 6 positive integers? There's only one way. 1 plus 1 plus 1 plus 1 plus 1 plus 1. Six times. Mm-hmm. So those are my initial conditions. Mm-hmm. But this time around, I need to actually use, you see, my pairs right here. These pairs right here, the n-1, n-1 is the same as with the Pascal triangle. The pair is the same. Let me just go back to this pair, n-1, n-1. But in the regular Pascal triangle, this is also n-1, which means that it's right in the previous row. N. Okay? In the partition numbers, numerical partitions triangle, this is m-n, n. So this is in a different row. It's not just one row above. It's n rows above. And it has to be the same, the same entry as the one that we're trying to do. So you just have to go up along the diagonal. So you're going to take the sum of, for example, here. So for example, if I wanted to know P62, in a regular Pascal triangle, I would just do the sum of these two. Yeah? But in this one, I'm going to do the sum of that one, and then I'm going to go 2 steps up. Mm-hmm. So in this one, and you can see it here. So if I wanted to get P62, I'm supposed to do P51 plus P6 minus 2, 4, 2. Mm-hmm. And that's 2 steps up. So I'm supposed to add this one plus that one. Make sense? Or for example, if I wanted to do P63, let me do it with a different color. So if I wanted to find P63, then I'm going to add that one, 2, I need to go 3 up. 1, 2, and 3. So I'm supposed to add this one to that one. Mm-hmm. And if I'm doing everything in order, then I should be fine. Now, if you get out of the triangle, for example, if I wanted to know these, if I wanted to know P32, I'm supposed to add that one to 2 steps this way, right? So I get out of it. That would be like P12, which is out of my triangle. All of those are zeros. Whatever is out of my triangle is a 0. Okay, because this is the number of ways to partition the number 1 to write write 1 as a sum of 2 positive integers. There is no way. Okay, so everything that's out is a 0. So in this case, this is just so I'm supposed to add that one to that one. So this is just 1 plus 0 equals 1. Make sense? Questions? So try to get it. Question.
It's fun.
Yeah, try to complete them. So I have these slides for the Pascal-like triangles in Canvas. So my advice, there are problems, scattered problems where you are asked to find the sixth row of the P numbers triangle or something like that. So my advice is everyone should try to complete these triangles. And I'll we'll continue with this next time, but everybody should try to complete the triangles, and all those questions, whoever got them, you have what you need. Okay, all right, guys, so time's over. I'll stay here for some more time in case you have questions, but please feel free to disconnect if you have to go.
Thank you.
Bye.
So thank you.
Professor, I did send you an email. I was just wondering if you got it.
Let me see. It was concept, right? Well,
Yes.
I didn't see you in a while. I saw you in my roster. I was like,
Yeah.
did you continue doing some? Oops, sorry. Did you continue doing some research?
I kind of was, just then school kind